Howdy everyone. In this video, we'll be discussing an example problem that applies Bayes' rule to a real-world situation involving COVID-19 testing. This problem will help you understand how to interpret test results while considering the test's performance characteristics and the prevalence of the condition in the population. Let's start with the problem statement. A new rapid test for COVID-19 has a sensitivity of 90%, meaning it correctly identifies 90% of people who have the virus, and it has a specificity of 95%, which means it correctly identifies 95% of the people who do not have the virus. The current prevalence of COVID-19 in the population is 1%. We'll be answering two questions. One, if a person tests positive for COVID-19, what's the probability they're actually sick? Two, if a person tests negative for COVID-19, what's the probability they're actually healthy? Let's define events and probabilities. Event A, the person has COVID-19. Event B, the person tests positive for COVID-19. Now, once we defined A and B as events, they have their own A prime, B prime complementary events, which is to say A prime will be the person doesn't have COVID-19, and event B prime or B complement will be the person tests negative for COVID-19. We are given the following probabilities. One, the prevalence of the COVID-19 in the population is 1%. In other words, P of A is 0.01. Two, the sensitivity of the test, P of B given A, or the probability of a positive test given a COVID sick person is 0.9 or 90%. The specificity of the test is P of B prime given A prime, or in other words, the complement of B given the complement of A. In words, it's the probability of a negative test given a healthy person is tested. And this is 0.95 or 95% chance. Where B prime, again, is the person tests negative event. Solving for P of A given B. We can use Bayes' rule to calculate this. This is P of A given B is defined by P of B given A times P of A divided by P of B. Here in the denominator, we used the law of total probability to describe P of B in terms of conditional probabilities. Now, if we substitute the values, if we plug in the values, what we get is that P of A given B is 0.154. Therefore, if a person tests positive for COVID-19 using this rapid test, there is approximately 15.4% probability that they actually have the virus, which is pretty low. If I take a test and it says that I have the virus, the test says that I have the virus, I want to believe that I actually have the virus, but there is 0.85% or 0.85, sorry, 85% chance that I don't have the virus, according to this problem. Let's solve for P of A complement given B complement. Again, we can use Bayes' rule, and we plug in the numbers for P of A complement given B complement is P of B complement given A complement times P of A complement divided by this expression, when this expression is using the law of total probability to describe P of B complement. When we plug in the values, we get that the probability of P of A complement given B complement is 0.9989, which is almost 1, okay, very close to 1. Therefore, if a person tests negative for COVID-19 using this rapid test, there is a very high probability, 0.99, that they're actually not infected by the virus. Let's conclude this example. When interpreting test results, it's crucial to take into account the sensitivity and specificity of the test, along with the condition's prevalence in the population. We've seen that because of the condition's prevalence is low, like zero 0.01, even if the test is highly sensitive and specific, the chance of having the condition after a positive test result can be low if the prevalence is also low. On the other hand, with a low prevalence and highly specific test, the chances of not having the condition after a negative test results are significantly high. Thank you very much. And if you have any questions, don't hesitate to ask me in class or email me. Thank you.